So I got v theta. Can you tell me what's the next step? This v theta at any theta. What's the next step? So this is, in particular, this is v theta circulatory at any theta. Can you tell me what's the next step? Apply theta 0 exactly, and then
Using that.
here this, right?
Put
Apply
down.
the Cotta condition. So let's do that. Can I do it here, or it would be very hard for you? Oh yeah, this one. Okay. Any question, please? Any question so far? Any question?
I didn't really understand why we're not summing the sphere itself plus the free stream or whatever to make a condition.
No, remember already, this is very good. And why we're not summing the motion? Why we're not accounting for the motion? We already did. We already accounted for the effect of the motion in the non-circulatory component. We take the effect of u, alpha, and h, right? And this is how we got the source, the strength of the source. We accounted for that. All what we needed to do, so this satisfied the no penetration boundary condition. All what we need to do now is not to disturb this satisfaction of the no penetration boundary condition. Which means whatever you're going to add to the flow, please make sure that the effect on the cylinder is tangential, it will not affect the normal. Because the normal is set to satisfy the no penetration boundary condition, it's set to maintain the motion, right? You see what I'm saying? So we already accounted for the effect of the motion, the free stream, or the entire motion in the non-circulatory. I don't need to account for it again.
So even if it's not moving, we will have a certain distribution that is making the no penetration condition valid too.
If it's,
If
therefore
it's
it's not moving,
Yeah, even if it's steady, it has a velocity where it's not moving up and down. Or
that's right. So if it's steady, it's not moving, then the source distribution will be 0. Okay? The source distribution will be 0, and here it will come with you naturally. So like I said, this is very important. So Laplace squared f equals 0. No penetration boundary condition. V normal is equal to V normal motion. And Cotta, law of zero total circulation. Right? I'll say blue here is non-circulatory, red is circulatory. Okay? So we already, how did I satisfy this here? Just by adding singularities that they naturally satisfy this guy, okay? So this was naturally satisfied. This guy, we did a lot of work to satisfy it. It was not easy. This is where we proved the very long derivation that we proved that the V radial is half at any theta, is half of the source at any theta. And V radial, we equated to V radial, the normal, right? Because the normal here is the radial for the cylinder. V radial coming from the motion. This is known from the motion. This is how we got the Q, the source strength. So we already satisfied this condition. Okay? We already satisfied in the sense that the cylinder now is moving radially the exact same way dictated by the motion. Okay? All the radial velocity coming from the source distribution is exactly equal to the radial velocity dictated by the motion. Okay, now I'm going to add a component. I'm going to add a vortex. That's fine. Please don't disturb this. So make sure that the radial component coming from this guy is 0, and this is what we did. This is what we did. Okay. So the D is, this is the homework problem. The D is selected to be this number to make the V radial is 0. Okay? So now the counter condition remains to be satisfied, and it's not about remain to be satisfied. It's my only way to get the strength of gamma. Gamma is still unknown, and I don't have any condition to get it. This is naturally satisfied. It's like 0 equals 0. This is naturally satisfied. This is naturally satisfied. This is the only condition that I can make use of to get gamma. There is no other way to do it. Okay? So V theta non-circulatory at theta equals 0 plus V theta circulatory at theta equals 0, this has to be 0 for the Cotta condition to be satisfied, i.e. for the U trailing edge to be finite. Okay? This guy, we got it last time, it was negative V 3/4. The normal speed at the 3/4 just happened to be like this. We derived an expression and it just happened to be the normal speed at the 3/4 cone. Plus, this guy, it's over there. We just got it here. Please substitute at theta equals 0, so this will be easy. So V theta circulatory at theta equals 0. So it will go away, okay? So you can see that this now, I can write it as x minus b over 2 all squared, right? Which means that this is negative gamma over pi b. This is x minus b over 2, x plus b over 2. So I have x plus b over 2 over x minus b over 2, okay? Yes, Amit?
Well, regarding the question that the students are asking, so why we are not adding the stream function of the cylinder?
You can add it, we'll not add anything.
Yeah, no, they are asking that why we don't add it in the F, at the top of that. Why we are just adding two vortices. So the reason is that we are superimposing the non-circulatory and circulatory. In the left-hand side of the Cotta condition, V theta non-circulatory equals 0. If you delete that, then you can add the F to this function and satisfy the whole thing in the F.
This is one way also of answering the question. It's as if, but he's saying that it's already taken care of here. So we have, this is linear equation, this linear dynamics. We always make use of superposition. So your flow field in general at the end, your flow field will be whatever coming from here plus whatever coming from here, right? And here is already accounted for the same way. Over there, we're just getting the effect of the vortex, the vortex pair. But again, what I'm trying to stress is that the Milne-Thomson circle theorem is just to make the cylinder as a streamline. It's just to satisfy this. So if you already have the streamline, you don't need to. Okay, so one quick here. So where should I do it? I'll do it here. So you have your cylinder, you have gamma here at a distance x, okay? And this is b over 2. Over there in the plate domain, you have the plate is from b, negative b to b, right? And the location of this guy will be somewhere here at a distance, whatever, should we call it, we should call it little x, but just to differentiate, I'll call it z, okay? So z is supposed to be x plus iy, here it's just x because y is 0. And we know the relation, right? The relation is the z is x plus the radius squared over x, okay? This is the Joukowski transformation. Whatever point here, you can substitute there to get the corresponding point in the plate domain. It turns out if you use this relation, I'll leave it for you to exercise it. You will find that x plus b over 2 over x minus b over 2, this is actually square root of z plus b over z minus b. You can try to play around with this relation and verify that. So this is here is negative gamma over pi b square root z over b, z minus b. And this is gamma at z location. Okay? Any question about that? Any question? So this is the tangential velocity of the cylinder at this particular point due to a pair of vortices. This vortex at a z location. What Theodorsen did is that, of course, he did not introduce one vortex, but a distribution of these vortices. Okay? Gamma wave. So the change is very easy. Is that I will replace here this single gamma by an integral. Okay? So this will be negative. It's already negative. 1 over pi b integral, and instead of a single gamma, it's gamma wave of z dz, right? And it's also a function of time. Square root of z plus b minus divided by z minus b. This is supposed to be 0, okay? So instead of single vortex, I have a distribution. Each one at the location z multiplies some square root that is a function of z. That's okay. I maintained it here. That's okay. Can you give me the limits of the integral? Anybody can give me the limits of the integral? Z goes from where? Z goes from where? So I'm integrating over the wake. Okay? So z goes from where? Oh, guys. Z goes from where? Does this start? Will you have a wake vortex here? Because this is on the plate, so the wake starts from where?
B.
From B. Until what? Where?
Infinity.
Infinity. Right? So here is your governing equation. What's the unknown in this equation? So just to stress, this is function of time. What's the unknown of this equation? What's the unknown? Come on, what do you think? I mean, there is no shame. I'm not expecting that you fully know these things. We're just discussing. Exactly, it's the distribution of gamma in the wake, right? And what is known? It's your airfoil motion, correct? So this is your input, aerodynamic input, and this is a partial output because I consider as my ultimate output is the lift. I'll get this and get the lift from it, okay? Can you give a name for this equation? Should you give it a name? I mean, it's not a very famous name, but should we characterize it? How we characterize it? It's the exact same thing we did with linear force theory. What's the type of this equation? Is it algebraic, differential, whatever, PDE, integral? What's the type of this equation? This is integral equation. So this is integral equation for what? Remember? Circulation. It's always like this. You get an integral equation for circulation distribution. Whether it's steady, it's unsteady, 2-dimension, 3-dimension, doesn't matter. Whenever you're using the method of singularities, there's always an integral equation for circulation. And it's always very hard to solve. Okay, here it's really hard. We cannot solve this for any arbitrary kinematics. If you tell me V3/4 is some function of time, no. We cannot. Okay? We have a particular solution. So I'm just reminding you that the angle of attack at the 3/4 chord is this guy divided by u infinity, right? Divided by u, or u infinity. Okay? So I'll just rewrite this equation as 1 over pi u b. Here is also the 2, whatever, or equals of this integral gamma wave z and t. And this is even harder than the steady one because the steady one was function of space only. This is function of space and time. So this is alpha 3/4, 2 pi alpha 3/4 as a function of time. this is your governing equation. Give me your effective angle of attack. Again, the 3/4 chord point comes to be the effective. Okay? Give me your effective angle of attack. Hopefully, if we manage to solve this equation, we'll get the wake distribution as a function of time and also space. Okay? I mean, we'll get to that, but it's not obvious how to solve it. And there is no analytical solution for arbitrary kinematics. I cannot invert this equation and get gamma wake as a function of zt and the alpha 3/4 as a function of that. This is very hard. I mean, it cannot be done. Okay? So this is the exact equation that Wagner derived in 1925 he solved it for step, but using a different spirit. He did not divide into non-circulatory and circulatory and this kind of stuff. He derived it using a different spirit. Okay? So he did it for step alpha 3/4, which means alpha 3/4 as a function of time is some alpha for time greater than or equal 0, and 0 otherwise. Okay? It's a step input from which he got the usual shape that is known, gamma wake versus time, some shape as a function of time. It levels off at gamma quasi steady. This is the value. And I want to tell you something. What is 2 pi alpha 3/4? What's that? Can you tell me? 2 pi alpha 3/4. What's 2 pi alpha 3/4?
Steady CL.
Very good. This is the steady CL. But if we apply it in an unsteady fashion like here, we call it quasi-steady. Okay? But it's the steady relation. So this is actually your steady CL. So you say quasi-steady. So you can think of your, this is your aerodynamic input. Here is the equation. It's as if A x equals B, you know? It's a linear equation, but the operator A is a very difficult operator. It's an integral equation, it's not a matrix. Okay? It's Ax equals B. My x are known as the gamma wake, and my B, which is the input, can be thought of as the angle of attack at the 3/4 is the airfoil motion, or the quasi-steady lift, or indeed, if you multiply by UB, this is the quasi-steady circulation. If you multiply by UB over there, this is quasi-steady circulation. They are all proportional to each other within a linear theory. Okay? Even the solution of Wagner, he did not get a function of time. We did not have this. We do not, up to this point, we do not have this as an explicit function of time. But we have it as a table. You give me your time, I'll give you, I'll give you the corresponding function. So we have some points. And later on, people developed an approximation for this function by explicit function of time. Any questions so far? So we did not get a useful thing, so we'll proceed to get the useful thing, right? I mean, this is not very useful. Luckily, Wagner solved it, and we have kind of points here. So for a step input, we know the solution. But other than that,